Hello and welcome to E233. I'm your instructor, Gregory Myers. In this video, we're going to take another look at our P2 project. Remember that it is a sample project. It may be a little bit different from the one that you are doing. This video is part of a larger series of videos focusing on the fundamentals demo, but it is also a separate standalone project. This video assumes that you have already created the project and that you've obtained and can understand the purpose of our P2, as well as having gotten the PowerPoint file that gives you some of the formulas that we're going to be using. Additionally, you want to take a quick look at the P2 sample.txt, which I provided for you, that basically just gives you some guidance of how you will communicate with the user. And then ultimately what we're going to do in this video is we're actually going to build each one of our functions. So let's go ahead and get started. I encourage you to go ahead and pull up the PowerPoint. If anything, make sure that you're comfortable with the formulas. These are not necessarily intended to be very complicated, but it just gives you a sample problem with which we can work on. So I'll leave that off to the side. And what I'd like to do is I'd like to start with our projectile 1D. And so you'll note in the sample file, I give you the how to communicate with the user, and also in the instructions, I sort of give you some hints about the input and output values. And so effectively what we're going to do in the Projectile 1D version 1 is we are going to capture from the user the initial height, and then from that we're going to calculate the T final, in other words, the time that it takes to fall and hit the ground, and then also the Vy final. And so we've got a couple of steps here that we need to do in order to accomplish this. And so let's go ahead and make a quick outline of what we need to do. And so first, we need to identify the input and output variables. And we want to go ahead and take a second to also include their data type. It's very important that we get familiar with this concept of not only the value of the data, but also the type of the data. And so once again, if you take a look at the P2 instructions, you'll see that, and you can also see it in the sample, that we have a decimal value for the input. And so in this particular case, what would make the most sense is probably that we use a double precision value. And so what we're going to do is we're going to have a variable double y init. We also need a few others here. We can have a t init, and we'll see that this basically just makes the problem a little more flexible, although we won't use it. And then we have our t final. We also have our vy init and our vy final. And then we need to somehow be able to use or store the acceleration. And so there's a couple of ways that we can go about doing this. We can either use this as a local variable, or since it is essentially a constant that can be used in multiple places in our project, what we would like to do is we'd like to come up here now above our function prototypes. And what we can do is we can simply create a define. And what we will do is we will define our AY as -32.2. Now remember that C does not specify or has no way of tracking units. And so what we want to do as we go along here is we want to provide to it sort of a reminder of what our units are. In this case, it's going to be feet per second squared for AY. And then we can do the same now for our variables. And this just helps with good documentation, create good documentation as we go along here. And so, sorry, our y init then is going to be in feet. Our t init is going to be in seconds. Our t final is also going to be in seconds. And our vy init is going to be in feet per second. And then our vy final is also going to be in feet per second. Now, we have declared our variables, but we also need to remember to initialize them. So must initialize, and it's good practice simply to initialize all of your variables, even though maybe later on they'll be collected by the user or used in an equation. It's good habit to simply go ahead and initialize your variables. Now we're going to be doing this in a two-step process here, first declaring and then initializing it. And just remember that if you fail to initialize these variables, you cannot trust the values that are in those variables. And so we'll start off with the y init. Now we are going to be collecting this from the user, but we'll go ahead and initialize it as 0. Our t init is going to be 0. Our t final for now is going to be equal to 0. Our vy init is going to be equal to 0, and our vy final is going to be equal to 0 as well. Now notice here I'm doing 0.0 because that is forcing or indicating that it is a double. Now, if you notice over in the sample file, I've provided a prompt for the user. Please enter a height, and I go ahead and give you this template here. You can go ahead and copy from it, or you can copy and paste it, or you can type it manually. But the idea at this point is that we want to collect info from the user. And we do that in a two-step process. The first is a print statement using printf. And in this case, I'm just going to say, please enter a height. And the idea is just to make a friendly message as well as informative. In other words, provide for them the units. In this case, then it's going to be feet, followed by a new line, and then a semicolon. And then we need to follow this up with a scanf. And a scanf requires us to specify the format spec of the data that we're attempting to collect. In this case, it's going to be %lf. And we're going to store this value at the address of our y init. At this point, that's all of the inputs that we need from the user. The rest we're going to calculate as we go along. In this particular example, it's pretty straightforward. We're also going to make some assumptions here. And these are not necessary assumptions in general. In other words, you can rewrite the formulas and you can have a different t initial other than 0 and a different vy initial. But just for this problem, we're going to assume that we're not throwing the object up or down. We're simply just letting it fall. And we also are ignoring the resistance due to air. So basically at this point, we're just dropping an object in a vacuum. So we're going to assume our t init and vy init are 0. And like I said, that just simplifies the formulas for us. Now, once again, go back over to the PowerPoint that I provided for you, and you'll see an equation for t final, and it's related to our y init as well as the acceleration. So what we want to do now is we simply want to solve for t final. So t final is going to be equal to the square root. I like to use an abundance of parentheses here. And for the numerator, it's going to be 2 times our y init. And that is going to be divided by our ay. And that is our constant that we defined earlier. At this point, what we want to do is we want to figure out how to display our values as well as calculate any additional values. If you'll notice over on the right, you'll see that in addition to our t final, we also wanted to have our vy final. So what we want to do is we want to calculate that from our v init. So vy final is equal to vy init plus ay times our t final. And this is why it was important to go ahead and include a vy init variable, even though we set it equal to 0. Like I said, with a little bit of modifications, and this can handle different scenarios. So if you go back over to the table, you'll see that we pretty much have everything handled that we wanted to provide back to the user. Once again, this sample is just intended to be sort of a guide so that you can understand what I'm looking for in a particular project. Now, as far as the output goes, we can leverage this sample. And what we can do is we can start off with a printf and a new line. And very carefully, what you can do if you want to follow it exactly, you can simply copy and paste what I wanted you to do in here, or you can manually type it, expand the number of spaces as needed per your own aesthetics. But fundamentally, what we want to do is we want to have a nice looking table for the user. Likewise, with the equal signs, it's kind of arbitrary, but it just allows for a nice looking table here. And in this case, what we want to do is print F, and we'll paste the bar, if you would, that's created by the equal signs. And then we're going to do that at both the top and the bottom of the table. At this point, you have a little more flexibility. And what I generally encourage doing is simply printing the input arguments first and then the output arguments to the user. So in this case, what we want to do is we want to look at our Y init, and we also want to specify the units. And the colon is technically optional. Once again, it's just for aesthetics. And you can tab over, or you can be careful with how the sample file does it. You can simply copy and paste from there. But what we want to do here is we want to leave enough space between the name and the values so that they don't run into each other and then cause our table to look strange. As far as the specific format spec that we're going to use for our printf, it's going to vary based on the projects. But in this particular example here, if you'll notice, I have asked for 4 decimal places. So what we want to do is we want to look at the total number, or the total number of spaces in the format spec. And a good example of this might be something like 8.4F. Once again, it will change based on the project, so you want to check the most recent project as far as the format spec that I use. But at this point, then we simply then want to print out in the table our Y init. Now we repeat this for each one of our values. And you'll notice here that we also have a Y final. Now our Y final can actually be calculated from our T final using the position equation. So why don't we go up here and we'll go ahead and add this as an additional variable. And it's just nice because it proves to us that it did in fact hit the ground fundamentally. And so we're going to go ahead and add a Y final variable. We're also going to specify that it's in feet. We're going to initialize it to 0. And then what we're going to do is we're going to come along here and we're going to calculate it. So Y final is going to be equal to Y init plus our VY init times our T final. And then the third term, once again, is from the PowerPoint. And there's a couple of different ways that you can go about doing this. You can either just simply go ahead and put in 0.5, or do 1.0 divided by 2.0, or 1 divided by 2. But in this case, we'll just go ahead and put in 0.5 times our A, Y. And then now we come to our T final squared in the third term, or the T squared in the third term. And we can do that 2 different ways. We can multiply T final times T final, or we can also use the POW function. POW function just allows for us to do exponentiation. In this case, we provide the base first. In this case, it's going to be T final. And then as a double, it will get cast to a double, even if we decide to do integer. But there is then our T final squared. You want to make sure that you have matching parentheses. You can see how NetBeans highlights this. And now we have our Y final. So we can add this now to the table. And I'm doing this sort of a little bit out of order, but I'm wanting to show you how you can build and grow this as we go along. And so once again, %8.4F followed by a new line. And then now we have our Y final. Once again, depending on the order that you want to present these in, we can do the T final first and the T init and the T final first. Doesn't really matter. Once again, follow the specifications for the particular project you're working on. And in this case, we have our T init. We're going to go ahead and keep the same 8.4. Just my double quotes there. and then the same for our T final. At some point, you're probably going to want to rely on copy and paste to speed this up, just keeping in mind that you want to shift the format spec appropriately. All right, so now we're on to our VY init and VY final. Hopefully at this point, you've started to see the pattern. And in this case, then our VY init is going to be feet per second, still keeping the same format spec. And there's our VY init. And then the last one in this particular table is going to be our VY final. Once again, just keep it lined up nicely. All right, at this point, we've written a moderate amount of code. It's probably was time even earlier to go ahead and build it just to make sure that we don't have any mistakes. Okay, so I encourage you to build often as you go along. This one was fairly straightforward, so it would have been obvious for us to find any mistakes, but I would definitely discourage you from going on to another function before building and making sure that it works. So at this point, we have a successful build. It's time for us to take a look at our main. And so if you recall from the earlier video, I simply went ahead and put in calls to each one of our functions, and then we put a printf statement in each one of the functions. Now, that's probably going to get a little excessive or a little noisy, especially as we add more functions. So what we'd like to do is we'd like to simply comment out the ones that we're not interested in looking at yet, and then go ahead and build it. At this point, you can go back to the command line, and you can go ahead and run your p2.exe. You're going to be prompted to please enter a height. In this case, we're going to follow along with the sample. Type in 100, and you'll see that I get a Y final of 0, -0. In other words, you'll see that there's a little bit of round off error. If we were to dig in and add a longer format spec for our Y final, you'll actually see there will be a small negative value there. Basically, what that's saying is very close to 0, except for the round off error. And then we have a T init of 0, a T final of 2.49. Our VY init was 0, and our VY final was -80.2496. So at this point, what we want to do is, now that we've got our Projectile 1D version 1 done, I'd like for you to go ahead and pause the video and go ahead and start working on the Projectile 2D version 1. And when we come back, we'll verify that you've got your code written correctly for both the Projectile 2D version 1 as well as the simply supported beam. We will then go through and show how we can turn on and off each one of these functions. And ultimately, in another video, we'll talk about how we will build and then test these. So at this point, let me go ahead and pause the video and go ahead and get started on your Projectile 2D version 1. All right, welcome back. Hopefully you had a chance to get your Projectile 2D version 1 working now. We're going to briefly go through it. Basically just expands on what we saw in the Projectile 1D version 1. Except now I have additional variables, not only for the Y direction, but also for the X direction. You want to leverage the PowerPoint that I've provided for you for this particular problem. You'll also notice that in the PowerPoint, the equation for T final, when you're dealing with two-dimensional motion, is a little different. Now, technically, we could have made some assumptions here, and we sort of did. Particularly, the assumptions that we're making is that we are on level ground. In other words, that Y init and Y final should essentially be the same. In addition, we are also making another assumption that our AX, or acceleration in the X direction, is equal to 0. And both of those are perfectly fine assumptions. Once again, the idea is just to simplify the problem ever so slightly, but still do something useful. And then the third assumption that we're going to make is that we start our timer at T init, much like we did in the first problem, and T init is equal to 0. So I have declared all of my variables up here in bulk. I will probably or should probably go through and add my units. So for instance, we'll have for our time is going to be in seconds. Our y init is going to be in feet. Our y final is going to be in feet. Our x init is going to be in feet. Our x final feet. V init. Now notice this is V init without direction, but it's still going to be in feet per second. Theta will be in radians, and our Vy init will be feet per second. Our Vy final will be feet per second, and our Vx init feet per second, and our Vy, or rather Vx final, feet per second. Now, I've went ahead and initialized all of my variables to 0, even though some of them we are going to be capturing from the user. Once again, just good practice. At this point, we'll follow the sample template, and we will prompt the user for both the velocity and the angle. And you'll notice that following each one of the print statements, there is a scanf that stores the value in the address of the appropriate variable. In this case, remember, that's what the ampersand is for. And in both cases, this is %LF because we're interested in capturing a value that we're going to store into a double. Now, remember from your physics or statics class that we want to break apart the initial velocity into its components. The cosine component is in the x direction and the sine component is in the y direction. What we want to do there is simply leverage the built-in functions that we will find in our math.h. As a matter of fact, if you do not include your math.h, you may find yourself with a warning down here in the output window, in which case all you have to do is simply include the math.h at the top of your source file. Now, continuing on, once we have our Vy init, we can use that to calculate our T final. Notice a slightly modified equation. And then from there, what we'll do is we'll actually calculate not only our Y final to verify that we did in fact hit the ground again at the end of the projectile motion, but we can also calculate our X final. Now, we could have made some simplifications here. In other words, we could have made the assumption that our Y init was going to be equal to our Y final. And essentially here we would be, if it was not the case, then we'd be calculating a delta Y. But I've included both the Y init and also the X init, as well as the Vy init and Vx init in both sets of the position equations for a more generic version of this formula that you can then tweak later on. Likewise, also for our Vx and our V final, we, in all four cases, we use our T final. And you'll notice here that I have created another constant that I have defined up at the top of our source file. In this case, our A underscore X is just simply equal to 0. Now, at this point, we've calculated everything we need to, and it's just back to printing the table. I've once again borrowed the template that we have, our sample.txt, and I've actually borrowed some code from the previous function to set this up. But basically what we do is we go through and we print out all of the input arguments followed by all of the calculated values or assumed values. And you'll notice here that I've included some spaces, a little extra white space between the printf statements. That does not affect our output at all. As a matter of fact, our output in the console is affected by our /n or the new line. Rather, these spaces in here are just for us as the developers to sort of break up the chunks of the table. And you'll see here that what I've done is I've simply just grouped all of my Y values together, as well as all of my X values together. It just makes life a little bit easier. At this point, then, you should go ahead and build your executable. In this case, we've got a successful build. And you'll come up here to our main. And if you recall from last time, we still had our Projectile 1D version 1 uncommented. And so what we want to do now is we want to comment this one out, and we want to run our Projectile 2D version 1. At this point, since we've made a change in our source file, we want to turn around and build it once again. And what we can do now is we can come over to the console, command line once more, type in dir, and you'll see there's my p2.exe. And now this time around, I'm going to get a different prompt. In addition to it telling me I'm calling Projectile 2D version 1, I want to simply enter in a initial velocity. And you'll notice I've given you some hints over here as to some values for your angle in radians, 0.7854. You can probably guess where I got that value from and why I picked that value. And particularly, you'll notice here that my Vy init and my Vx init are roughly the same. What I did is I picked essentially the radian value for theta equal to 45 degrees, so that way I could recognize that we had in fact set up the formulas correctly. Quickly looking through the table here, you'll see there is our T init, our V init, the theta, and so on, as well as our calculated values. And particularly of interest to us is the fact that our X final is 310.5590 feet. Once again, don't focus too much on the format spec for this particular example. It's going to be tied to whatever version of the P2 project that you use, and you can adjust the decimal places from there. So assuming that you've got this one working, what I'd like for you to do is once again pause the video and then come down here, and you'll see I've already started some notes here on our simply supported beam to sort of help us along. And what I encourage you to do is once again pause the video and simply go ahead and give it a shot yourself, and then come back to check to see how you did. All right, so welcome back. Hopefully you've gotten your simply supported beam now working correctly. Let's go through this one, make sure that you understand how each of these pieces work. Much like in the earlier examples, we first declare all the variables, and then we follow it up with an initialization. Let's take just a second to include the units in here to make sure that we understand the problem. The W is the weight in pounds. The L represents the length in feet, and the A, or the length in feet of the entire beam, where the A represents the distance in feet from one of the endpoints to determine the relative load on each of the reaction points or the reaction forces. Then we have our R1, which is the reaction force at P1 or one end of the beam. That is also in pounds, and an R2 is in pounds, and our A is measured from our P1. So we initialize all of these values to 0 from the sample input output file that I've provided. You'll see the prompts that I want you to give the user to please enter the load. We store that into our &W, or address of the W variable. Likewise, with the length of the beam, we store L, and we store the location of the load in A. Now, before we go any further, we want to talk a little bit about these variable names. They are perhaps poor, you could argue. The only reason why I use these single letter variable names is because it's pretty common for this type of problem to use these, particularly the R1 and the R2, reflect the reaction forces at P1 and P2, but also provided some accompanying documentation. I only mention this because sometimes short variable names are useful, particularly when they follow some sort of natural convention. For instance, we all know the Pythagorean theorem as a squared plus b squared equals to c squared, and we can, of course, just simply use those and somebody would understand what we were doing. Now, from here, we also want to make some assumptions here because we're doing no validation or error checking on the data. That comes in later videos, but we're going to assume a couple of things. Number one is that our beam length is greater than 0, that our A resides somewhere on that beam. In other words, we've loaded the beam somewhere on the length of the beam. We would technically need to check this before we did the equations for R1 and R2, just so that it actually made sense. And then we follow this up with, once again, a nice little table that I've borrowed somewhat from our sample, but also from some previous code. And I simply just print out the arguments that were provided by the user, or the values that were provided by the users first, and then the ones that we have calculated. So at this point, what you want to do is you want to go ahead and build it, make sure that you've got a successfully built executable with this function working, or at least we believe this function works. We go up here to our main, we comment out the previous function, and we uncomment our beam version 1, and we build it. And we once again get a successful build. We come over here to our console, and we run our p2.exe, and it's prompting us for the load in pounds. I'm going to follow our example here. We'll actually do a couple of examples just as a sanity check. There's going to be 100 for the total load for W. The beam length, I'm going to follow example 10, and then the location of load in feet. So it's actually going to be 0.4 feet. And did this one somewhat intentionally because I wanted to emphasize that if you and a friend were carrying a sofa, if you were P1 or the first person, you ended up getting the majority of the load. In other words, you got 96 pounds out of the 100 from the load W. The other assumption that this one makes is that the beam itself is weightless. Let's run this one more time just to make sure that we do believe what's going on. This time around, we're going to check the load with 100, 10 for the total beam length. But the difference is going to be, I'm going to put in 5 for the location of the load, in which case you'll see that R1 and R2 are in fact equivalent or equal because we have put the load at the center of the beam. So hopefully this one also makes sense now, and you've confirmed that your formulas work correctly. I'm going to go ahead and stop the video here because I'd like to pick up with the third video in this series of how then you would actually go ahead and automate this testing or use input and output files combined with a batch file. So as always, if you have any questions, comments, or concerns, don't hesitate to ask, and thank you for watching.